Okay, so today we will discuss 5G. Okay, we dedicate ourselves to discussion of 5G because it's the most current version of the cellular network generation, right? So in terms of the semester, okay, we getting close to the midterm, right? So after this, okay, there'll be one big topic left, okay, and it will be quite theoretical about queuing theory. Okay, most likely we'll span a couple of classes. Okay, until the end of the until the midterm, right? And all those topics that we cover and will cover next, okay, will be on the midterm. Okay, so here's the outline of today lecture. Okay, we review the evolution of subsequent cellular network generations. Okay, because we already talked a little bit about it in when we discussed 3G and 4G, right? And then we switch gear to dedicate ourselves to 5G. Okay, talking about various aspects related to service categories, use cases, and um, I would argue most exciting enabling technologies. Okay, and then we conclude with the network architecture for 5G related to its deployment. Okay, so again, cellular networks, they come in generations, right? Depending on the underlying technology at the time of their inceptions, right? So as you can see here, we've gone through the major 5 operations. Okay, important milestones for the subsequent generations are stressed here at the bottom, right? At the beginning, right, the first generation cellular networks were all analog uh, networks, right? So what do I mean by that? Okay, the network and also the devices are designed using signal processing and data communication based only on analog signals, right? So in other words, the information is was not digitized, right? That started to change in the second generation, okay, where you see some part of the traffic from the users that were digitized, right? Before the uh, packetization of suitable data traffic from the users, right? So again here, when we talk about digital and digitalization and packetization in 2G and 3G, remember it's only for part of the user's traffic, right? Related to the data use because the cellular networks, one major use case is for voice telephony, right? And you all know that before 4G, right? Some of the voice, the majority of the voice calls would be carried through the old telephone network, right? That is a circuit switching network instead of the internet. Okay. So the main difference here is um, for 2G, the internet was not there, was not quite there yet. So there's no concept of packetizing user data traffic to be passed through the internet, right? Internet started to be used, okay, around the time of 3G. So that when the uh, part of the user traffic related to the data uses are packetized and sent through the internet starting from 3G, right? But as I said, the voice traffic is still going through the legacy home telephone network, right, in 3G. The convergence the convergence of both voice and data traffic all over the internet started from 4G, right? That we already mentioned last week, right? And now we moving to the era of 5G, where of course, for every generation updates, right? People would definitely want more bandwidth, more maximal rate, right? But as you will see, another motivation for the construction of 5G cellular technology is to allow the users to be able to afford wider application areas because more and more devices will be connected to the internet and also the cellular network, right? So you will see emerging uh, application areas involving some new internet connected devices, okay, like sensors, other smart devices, okay, that will require the network to be much more capable to support these wide-ranging application areas, okay. We will talk more about uh, the different use cases, okay, for which the 5G cellular network is designed, okay, shortly, okay, in which case, at that point, you get more concrete ideas about these emerging application areas. Okay, again, every time you go to a new generation of the network, right? So basically, there are canonical metrics, right? That should be targeted to be improved, right? Of course, faster peak rates, throughputs, okay, increased traffic volumes. Volumes is related to both the peak rate and the amount of users you can support, right? So it's similar to, I would say, capacity, right? The delay should reduce, right? And in terms of availability, okay, or reliability should improve as well, okay. We would like to improve coverage, okay, and enable new service categories and capability as well, right? Improve security, okay, and support for higher mobility because um, people are moving faster than in the past, right? Because the people are moving more, right? The the vehicles or the trains on which the user are on are moving faster. That's why the network has to be more capable to support more severe mobility use cases, right? And of course, okay, people would wish their devices to last longer uh, before the next charge, right? So in terms of the network engineers, we should try to improve the energy consumption as well. Okay. Okay. To understand these different metrics, okay, there are some important to understand these different criteria, right? There are important quantifiable metrics that you can study, something like call setup success rate, right? Call drop rate, retainability, okay, mobility, maybe a bit vague here. I would say the first three are more quantifiable, and then coverage, right, which reflects the availability of network signals in a given area. Capacity is related to traffic volume, right? Quality of service, okay. This notion of uh, figure of merit depends on the application under consideration, right? For example, if you talk about voice application, you have a certain QoS, quality of service metric. Talk about data application, there may be other quality of service metric, right? Another more subjective is the user experience, okay? uh, Figure of merit, okay? Throughput and latency are quite quantifiable, right? Because this first can be measured in megabit per second, gigabit per second, per user, okay? And then latency can be measured quite precisely in the unit of millisecond, for example. So again, I go over all these different G's as a review in uh, in a quick round. Okay, so here first G is only voice communication, no data, right? And all signaling are done using analog signal, right? And of course, the traffic will go through the circuit switch network, right? Uh, the major contribution for this one is to allow users to call wirelessly, right? That's the only major contribution, okay? But you can see the device itself is quite cumbersome. Second G started to see emerging data applications, right? Like SMS, right? In addition to voice application, okay? And but the voice the traffic still goes through the circuit switching network because the internet was not ready, was not fully there and not ready to carry traffic for the cellular networks, right? Then starting from 3G, we see significant use, significant offload of the data traffic on 3G network in particular through the internet, right? But the voice traffic is still going through um, the edge of the cellular network, 3G network, and also through the legacy core of the home telephone network, right? Then starting from 4G, we see convergence, okay? An important innovation here is a new multi-access protocol called orthogonal frequency division multiplexing, right? Additional modulation schemes are also used, right? So here, regardless of whether your traffic is voice or data, everything will have to pass through the internet. And as a consequence, this is the first generation at which the cellular network becomes full IP. Yeah. So even if you make a phone call, right, your traffic has to pass through the internet. So a lot of time that is called voice over IP. Okay. And as a consequence, you see emerging new applications where um, the application makers they make uh, voice telephony purely internet native, right? By that I mean you don't need to use a phone anymore, right? You can just open an application, whether in the form of a native application or a web browser, something like a Skype, right? And then you can use it to call any available uh, uh, phone number in the world, right? Given that you have enough funding to pay for your subscription, right? So you can see major differences between 3G and 5G, right? Speed improvement, latency reduction, right? I would say the technically, uh, the arguably the most important innovation is in the multiple access mechanism, right? Where you go from CDMA. Remember, we learned about CDMA, code division, multiplexing algorithm, to OFDM, okay, in LT in 4G, okay. And you see new emerging applications in 4G, as I already mentioned, because of the improved network capability, right? And it's, I would say, it's simplify the architecture because uh, it's not like a patchwork of two major networks anymore. Right now, there's only one uh, core network, which is the internet, okay? And the rest of the parts of the 4G network will be designed with that harmonious principle in mind, okay? 5G, okay, is our current generation, okay? This is aimed to improve everything, right? Better uh, throughput, lower latency, okay? A major improve in capacity, meaning supporting more users with their with more data rates as well, right? And these are there to enable new challenging applications, okay? Canonical ones are something like smart cities, employing maybe 1,000 or 10,000 of sensors, okay, that integrate important data in real time, okay, to be processed and to allow the city planners to manage their cities in a more effective manner, right? Autonomous vehicles, right? Of course, these are so-called self-driving cars, right? The reason why cellular networks are so important for this type of emerging vehicle is that the vehicles, they have to know their environment, right? And because they are always outdoor, right? They have to have a way to connect to network that can get them real-time information about their surroundings, right? Whether it's gonna be the road or weather condition or information about other nearby cars, right? So that's why it's very important that these vehicles get the best support from the 5G cellular network. Okay. Um, Immersive AR VR, of course, video contents, right? Requiring a lot of bandwidth, right? That is also challenging. And because these applications are immersive, right? Meaning that the latency requirement is also very stringent, because if the network introduces a large latency, then the user for this application may get nausea. Okay. Other type of applications uh, require very high reliabilities, right? Some applications dealing with people life, like healthcare, for example, remote surgery, okay, and others. Okay. So As a bottom line, okay, 5G, you should expect 10x in speed, right? Up to 10 gigabit per second. Latency could go down to level of 1 millisecond, and capacity is million devices per square kilometer. Okay, these are basically uh, um, rough uh, uh, ranges of the numbers. So the real numbers may be different depending on specific providers we're talking about and specific areas. Okay. In terms of the diagram, right? Uh, you see a study conducted by this organization, Association of Radio Industries and Businesses, right? That evaluate different metrics for the subsequent generation of cellular network, starting from 4G in black, and then there was the intermediate release 4.5G before 5G. So you can see significant improvement in all important uh, metrics that are shown here. Okay, another table to give you some better idea of the picture surrounding the improvement. Okay, so here for the peak data rate, okay, you can divide further into upload and download. Okay, both should improve, but you can see that um, uh, the download speed is typically the maximum download speed is typically higher, right? Because most the traffic will be in the download direction. Uh, both increase about 20x, okay, from 4G to 5G. User experience data rate, okay, peak spectral efficiency, okay. Spectral efficiency, remember, this is related to both peak rate and also the number of users, right? Because this is a maximum the effective use of the frequency, because you don't just measure the peak rate, right? You offset that with how much spectrum each user using. And the idea is that if you look at the same maximum rate, right, you should attain it with the least uh, uh, size of the spectrum as possible, right? Because if you save the spectrum, right, then the entire bandwidth offered by the network can be used by the other users, thereby enabling better capacity to the entire user. So you can see significant improvement in the peak spectrum efficiency as well. Mobility, you can support faster user. Okay. Latency, again, canonical target is to go down to 1 millisecond. Okay. You don't always get to 1 millisecond in all cases, but eventually uh, we want the new network to be able to support important use cases at requiring latency at the level of 1 millisecond. Okay. Improvement in connection density as well. 10x in energy saving, right? And about 100x in mobile data volume. Okay, in terms of bit per second per square kilometers. Okay, any question, comments? Let's see how. Okay, you want to break now or a little further, because we haven't passed 1 hour, right? So let's go a little further. Okay. Next, we talk about service categories in 5G, right? So you see, as we have seen, for every updates of the cellular network generations, right? Every time there was an update, there were new emerging applications, right? Like from 1G to 2G, you start seeing SMS, right? 3G to 2G to 3G, you start seeing something like voice telephony, right? Yeah. And then 3G to 4G, you see even more applications, right? So now it makes sense that when you want to go to from 4G to 5G, we should have some in application, the idea of the emerging in applications in mind, right? And these target emerging applications uh, will be related to the service categories that we are talking about now. So basically, the 5G network aim 5G network aims to support uh, three diverging challenging application areas. Okay, one is called extreme or enhanced mobile broadband, right? The way you should think about it is that here is like 4G at the maximum speed uh, that is on steroid, right? So whatever you can do on 4G, for the maximum speed, okay, you should get more for 5G. That's EMBB. Okay, something like um, real time gaming, okay, over the internet, right? Virtual reality, augmented reality application, right? These are all come with real-time video contents, right? Requiring a lot of uh, maximum data rates to support the applications, right? Another important service category in 5G is the one that focuses very much on the latency, right? You want to go with the lowest latency as possible. And in addition to that, okay, the communication should be extremely reliable. Okay, what do you think are suitable application areas for this? That the communication should be with very low, extremely low latency and extremely high reliability related to cars, right? Because you don't want cars to get into accidents, right? If the cars are not responsive enough, or at some point they are disconnected to the network, right? That might lead to uh, catastrophic accidents, right? Something like the support for the communication of smart vehicles from and to the infrastructure, right? Okay, the same service category can be useful for other critical uh, application, something uh, life-threatening like remote surgeries, right? Because you want the latency to be very low so that the surgery that is performed remotely can be done in a very precise manner to save life, right? Okay. So the primary concern for this service category is extremely high reliability and extremely low latency, right? The third service category is related to Internet of Things, where uh, more and more small devices are connected to the internet, right? So here you be talking about application related to massive IoT deployments of low energy efficient sensors around geographical areas, right? For suitable applications like smart cities and logistics, right? Something like smart factories, right? Where you want to get the sensor data from all the factory devices, okay, to be able to orchestrate the factory in a more efficient and autonomous fashion, right? So here is a more concrete picture of these three service categories and how different specific applications map in terms of these three service categories, right? So like for EMBB, you see something like uh, based on high density video contents being very close to uh, the ideal of EMBB, okay? For URLLC, okay? Of course, the primary specific application is autonomous vehicle, right? But there are other applications that could be supported by the network design for this URLLC service category as well. And of course, for massive machine type communication, primary application should be smart city. Okay. Okay, let's go over each of these in a little more detail, right? So first one should think of it as being a maximal 4G speed on steroid, right? So here, this service category is designed to deliver exceptional mobile broadband experiences for the users, right? This is a major cornerstone of 5G services, right? And the peak rate should go peak download speed up to 10 gigabit per second and beyond. Okay. And as I already mentioned, this is suitable for applications related to video streaming, virtual reality, and augmented reality, right? To be able to support this service category, okay, the network has to be designed to increase its capacity significantly to handle high user density in crowded area and to have consistent performance for many users simultaneously with reliable connectivity in populated area. Something like, you know, extreme or enhanced mobile broadband supporting multiple close by users in a very small region, something like a sports stadium or at a concert hall, something like that can be classified as suitable for EMBB. Okay. Okay, in terms of technologies to enable this service category, we talk more about technology enablers in the subsequent part, but this one we give you just an introduction. So here to increase everything we talk about, right? Uh, 5G employs the addition of new spectrum, right, including millimeter wave bands and some unlicensed spectrums. Okay, some multi-antenna techniques are being used, like beamforming, right, and MIMO. Okay, and because we integrating multiple spectrums together to increase the maximum rate and the capacity, 5G needs uh, uh, a good spectrum toolbox to deal with this spectrum integration as well. Okay. in terms of the air interface, right? Uh, 5G employs some new techniques to handle ultra dense networks, something like device to device communication, and dynamic RAN. Okay. So this picture shows the use of multi input, multi output antennas for communication to improve the data rate, right? So here for the cell tower, instead of using a single antenna, you see multiple antennas, okay? And even on the small devices, right? Something like smartphone, nowadays inside your smartphones, there are multiple antennas. Okay, next one is URLLC. Okay, again, key is here is high reliability, low latency, as low as 1 millisecond. Okay, high reliability, okay, means 99.999% network should be uh, available, right? And communication should be uninterrupted. Okay, and these are definitely for mission critical applications, right? Like autonomous vehicles and remote surgeries, industrial automation for real-time control systems, right? So how can the 5G network enables this extremely low latency? Okay. Um, there are several techniques that are used by the 5G network to reduce the latency to the smallest possible level. Something at the high level are like caching, right? The network can cache the contents closer to the edge, right? Uh, and to the users to further reduce the latency. 5G also make the control plane simpler for this service category to further reduce latency, because control plane is about what? Control plane is about handshaking, right? The bulkier it is, right? The more rounds of handshaking has to be done before the session can be set up for data plane. So if you make the control plane leaner, uh, the network will reduce latency. At the radio level, okay, uh, you can see techniques that are being used like interference mitigation, diversity in communication, and mobility prediction using content information. And also, if you do direct device to device communication, the latency can be reduced as well. Okay, this is a picture of the latency. Okay, basically, when we talk about 5G, we should aim for the air latency to be at the minimal of 1 millisecond, because remember, for the end-to-end application, there will be more subsequent latency that are added up, right? So if you target 1 millisecond for air, then it will improve the end-to-end latency for the final application as well. Okay, last service category related to IoT. So here we're talking about applications related to massive device connectivity. And by that, I mean a lot of devices connected per area, right? Something like 1 million devices per square kilometers, okay? Because there are several devices, right? Most of them are designed uh, to be uh, deployed for a long time, right? So that means their batteries have to last a long time. So the network should support low power communication to these devices. And the reason why this low power and massive device connectivity can be trade off is that these devices, okay, often require very low data rates, right? Because if individual device are communicating with very high data rate, then if you have million of device, then the capacity will exceed the idealistic capacity of 5G, right? But when we talk about this type of application, oftentimes individual device uh, transmit at very low rate, right? But uh, there are many more of them, right? And of course, the cost is another important consideration for this type of application as well. Okay. So again, you see several techniques and enablers that are being used, right, to make the control for MMTC, make the control system leaner, okay, using caching, right, and aggregation to reduce transmission and increase battery life. In terms of the radio, okay, you can use something like relaying for coverage extension. So in this picture, you see, okay, the typical communication between various sensors to the 5G network, right? So here, to reduce transmission at the intermediate level, the user can deploy an aggregator to lump up communication from multiple sensors before combining it to the network, right? Some sensors may be communicating directly, right? Further uh, saving the battery life and also offloading from the network, right? Allowing other devices also to use the 5G network, right? And as a consequence, the entire network can support more and more devices. Okay. So here the diagram representing these three service categories based on different important metrics, right? EMBB in particular, focusing on network energy efficiency, area traffic capacity, peak data rate, user experience data rate, spectrum efficiency, and mobility. And of course, Ultra UILC focuses on latency and availability, right? Whose one proxy is to support high mobility users, right? Some application like autonomous vehicles moving at very high speed. MMTC primary focus is on connection density. You can achieve very high connection density because you can trade it off other metrics. Okay. Another pictures to summarize all these three service categories, including focus, use case, and different levels for the different metrics we are talking about. Okay. To enable all these service categories, right? So as I already mentioned, 5G integrate a lot of spectrums, right? So for EMBB or XMBB in particular, uh, a lot of spectrums are being used both under 6G and above 6G. Okay, for EMBB in particular, because you want to support very high bandwidth, oftentimes you need to use large contiguous bandwidth. Okay, and that often will require the use of unlicensed bands. Okay, MMTC. Okay, often typically the spectrum at the low frequency is preferred because the data rates can be lower than the other service categories. Spectrum with small bandwidth are okay. Okay. So in this service category of often licensed spectrum that are stable are preferred. Okay. For UILC of application require exclusive or high priority accesses. Okay. And because you want extra reliability, oftentimes you need to use um, frequency diversity to enhance the reliability by replicating the same communication across different frequency bands. Okay. Any question, comments? Okay, so here we will talk more about specific use cases related to the three service categories that we talk about, right? So this picture shows you important use cases, right? We talk about autonomous vehicle ready, remote surgery, okay, virtual reality, okay, factory automation, but there are other important application use cases here as well, something like smart grid, high speed train, okay, with the users being in high mobility, right? Um, emergency communication, which is very mission critical. Stadium and shopping mall. That's what I mentioned about a lot of users using a lot of bandwidth in a very confined space, right? So let's look at different requirements for these different important applications. So something like autonomous vehicle and factory automation uh, will fall into the URLLC category, right? You see primary requirements on the latency and availability, right? Um, high speed train, okay, a lot of um, uh, traffic volume density, right? And very high throughput, right? Because people are a lot of people are in the same train, right? Using a lot of data, right? VR application as well. This in the EMBB category. For MMTC, you see 1 million device per kilometer for connection density. Uh, reasonable availability and um, very high energy efficiency, right? Because these sensors, they'll be deployed for a long time, okay? That's part of the reason why we want to use spectrum with lower frequency as well, because the signal processing for signal with lower frequency can be designed easier to enable more energy saving. Okay, and of course, in terms of area, okay, you see a lot of emerging applications in healthcare, automotive, and transportation, entertainment, and media, right? So here is a general picture of different spectrums that are being used, right? So you see the lower the frequency, the longer range it will cover. The one in green will be what we call macro cell, right? And then as you start to move up in frequency, you get to a shorter and shorter range, okay? The one in blues are including the new millimeter wave spectrum, right? With very short range, supporting a very small area. We call it small cells. Okay. So here the idea is that you already have macro cell, right? So if you want to improve traffic density or capacity, you employ these smaller cells inside the macro cell to boost the capacity. And of course, this smaller cell can use this new spectrum with very high frequency. Okay. All these capabilities of the 5G network, okay, did not come out of the blue, right? There are several innovations that are being used. Okay. In this section, we talk about them in particular. Okay. These are just some examples. Okay. The full list is here. You see innovation at all layers, right? Starting from the physical layer, introducing new spectrums, right? Innovation in signal processing, employing multiple antennas, beamforming, innovation at the network level, right? Of uh, making some network function into software modules to allow the operators to slide network into different services. Okay. Another important network innovation is edge computing, right? Caching contents closer to the users to reduce the latency, right? Okay, let's talk about the introduction of a new important spectrum called millimeter waves. Okay, these are spectrum in this area larger than 26 gigahertz, right? The reason it's called millimeter wave is because if you compute the wavelength, right, it's in the level of millimeters, right? And you want to add new spectrum because you want to increase the capacity of the network, right? And this millimeter wave band has a very high frequency, right? That can support high bandwidth for high data rate. But the trade-off is because you go with very high frequency, the range can be lower than the other spectrum, right? So you have limited coverage and susceptible to being blocked by obstacles. So you have to deploy this spectrum in a smaller area, right? Like the picture that I showed earlier here, you can deploy this millimeter wave band for small cells, okay, uh, that are appended to the larger cell to increase the capacity. Okay. Sometimes these are called ultra dense network because you want to make the network very dense, supporting a lot of users that are very data hungry. Okay. Another challenge that come with millimeter wave band with very high frequency, apart from the limited coverage, right, is of course the susceptibility to blockage. And another important consideration is the front end consideration, right, where the front end processing that are required for this high frequency will be more challenging to do at lower cost and better energy efficient. Okay, that's part of the reason why for something like MMTC, you want to go for low frequency because the front end signal processing is easier. You can decide devices based on this lower frequency to save battery, okay, and at lower cost. Here's another picture of some new spectrums being introduced. Okay, so you see this millimeter wave band. Some are share license. Okay, some are unlicensed. Right. At the low frequency, uh, the communication can be done at lower cost and at a longer range. Another related solutions that can be integrated into the millimeter wave deployment are related to beamforming, okay, using multiple antenna to increase the coverage and provide seamless connectivity. In terms of front end, okay, you can do some mechanism like phase noise mitigation to reduce the cost and save more power. Okay. And because these millimeter wave are deployed as a boost to the macro cell, right? So oftentimes you need to decide to interwork with the lower spectrum, right? To increase robustness, right? And faster system acquisition. MIMO, as the name suggests, this is the use of multiple antennas, okay, at both the base stations and devices. Of course, at the base stations or cell tower, right, it's larger, so you can use many more antennas, okay, than in your smartphones, okay. These are used to increase capacity, improve coverage and speed, and you can use multiple antennas to optimize for spectrum use and allowing faster data rate, okay, thereby improving throughput and reliability. And also because you have multiple antennas, right, you can uh, you can use it to multiplex across multiple users to reduce their interference, okay, allowing more and more users to share the network. Of course, all these are not uh, coming out of the blue. You have to design the signal processing techniques to enable efficient use of these multiple antennas, and that is done in hardware. Okay, there can be many configurations, right? Of course, SISO is without using multiple antennas, single input, single output, but you can use multiple antenna both in either end or both ends, right? You can use here if the communication from this uh, transmitter with two antennas to a receiver with just one antenna, we call it MISO, multiple input, single output, right? The other way around is CMO, and the full-fledged version is MIMO, right? And of course, you can use more than two at either end. Another important ways to use multiple antenna is to use them to focus your signal in specific direction, right? To improve signal strength, reduce interference, and increase the range, right? Because you make the signal more concentrated. Right? This can be useful for dense urban environment, uh, and also can be useful to improve coverage. Right? Moving on closer to the network level, right? So here we again starting from 4G, everything is connected to the internet, right? So here you have the part of the cellular core infrastructure that are connected to the internet as well. And an important innovation for 5G is to allow the network operator to slice the network to create essentially different isolated virtual networks within the same physical 5G net environment, right? This is similar to the fact that you can run uh, uh, virtual networks, for example, on your laptop, right? To this end, each slide or each virtual network can be customized for different use cases or service categories, right? Depending on their suitability. And this is there to support diverse applications and industries with different needs. And because you do it in software, right? This allocation of different virtual networks can be programmable and customized, can be done more dynamically, depending on the different and changing application requirements. So you see the three important service categories, okay? And then the network, 5G network can be sliced into different slices, okay? Supporting different application in varying service categories. Another important network innovation is to use the so-called edge computing, right? What do you mean by edge computing? Remember, the network is split into edges and core, right? So the closer you come to the edge, the closer you are to the users, okay? And the reason why you want to go closer to the edge is because certain applications would require you to reduce the latency, right? So this is a concept of bringing the data processing closer to the users or end devices to either offload the latency, to reduce the latency, or offload the traffic from the core of the network, right? So this can be useful for applications in the URLLC service category, right? Ultra reliable, low latency. And this will also help reduce network congestion as a whole and ensure faster response time. Okay. So here's a picture differentiating the uh, different level of complication. Okay. The edge computing is very close to the users. Okay. The further you go into the core, right? Uh, the larger latency you may introduce. As a consequence, people often talk about cloud computing going deep into the core and also the intermediate level of the so-called fog computing, okay, at the middle level between cloud computing and edge computing. In the next innovation, okay, the core networks of 5G are also virtualized, and also made cloud native, right? So this is the concept of virtualization and containerization of network functions as software other than relying on dedicated hardware. So as you can imagine, software are more flexible, right? And more easier to deploy. Okay. So those are the primary benefits of making the core network virtualized and cloud native, right? To this end, important frameworks called network function virtualization and software-defined networking are being used. Okay, you get a chance to learn more about them in some other courses like NetCentric. Okay. This virtualization also allow operators to allocate network resources dynamically and also on demand, okay, improving cost effectiveness and operational efficiency. Small cells, okay, again, think in terms of the canonical deployment of these millimeter wave spectrums, right? You want to deploy it in a very small, in a smaller area than the other spectrum bands. So these small cells are short range base station. Okay. As a consequence, these base stations are smaller than the base station for macro cell. They use less power. Okay. You can deploy more of them than the macro cell base stations. Okay, this will allow user to connect more frequently and better, particularly in urban and dense environments. Okay, and you want to deploy these cells at the smaller range to uh, to to use the millimeter wave, right? Because the millimeter wave, they don't go for a large range, right? So you want to use it in a very small area. And because the area is smaller, you can support lower latency. But the challenge is that you have to deploy more of them, right? So if you have one macro cell, it's one macro cell for a very large area. If you talk about small cell, okay, in a macro cell, you need to deploy many of them. So the picture will be like this. You have a macro cell covering the entire area, okay? But depending on the requirements, right, for a very specific area that requires a lot of capacity, you can deploy smaller cells accordingly, right? Some application like stadium, sports stadium, okay, or and a large uh, office building, right? Then with a lot of usage of data rates, you can deploy smaller cells to support these high data rates. Okay, some AI and machine learning techniques are also used in 5G network to predict loads, automate network operations, optimize data routing, and improve security. Okay, all the use of these different spectrums integrated into the 5G, okay, uh, is called the 5G new radio, right? Because the radio will be different from the one that is used for 4G, right? So this is a radio access technology that defines the air interface of 5G, okay? So you see use of diverse set of spectra, right? Like ranging from license share, license, and unlicensed. Okay, what are the difference between license share, license, and unlicensed spectrums? Do you know the differences? When we talk about, let's say, licensed and unlicensed spectrums, how are they different? Why are they called licensed? Why are they called unlicensed? Pardon? License from whom? License mean you have to pay for the license, right? So unlicensed spectrum like Wi-Fi, right? You don't need to pay anything to use Wi-Fi, right? Why do you have to pay your cellular provider? And why don't you have to pay for your Wi-Fi provider? Because Wi-Fi is based on unlicensed spectrum, right? The radio spectrum that is being used, the provider, they don't need to pay for it. But for the cellular network, uh, they uh, they deploy some licensed spectrums, right? They have to pay for the spectrum, so that's why the user need to pay them back. So the question is, from which organization these providers are licensing the spectrum? Do you know? Have you heard of the process called spectrum auctioning? Have you heard? They do it every a few years or so, right? Yeah, so the providers, they have to auction to buy license spectrum from the government, right? To make sure that the government get the best and fairest prices, okay? Because these are public resources, right? That are supposed to be used by citizens. So the government take a hold of it and auction it off to license providers. Okay. So you see diverging type of spectrums. Okay. So license share and license means if it's like exclusive license, it means that for that spectrum, there's only one provider that is licensing it. License share mean for that license spectrum, maybe there are multiple providers that are sharing it. Okay. Anyone can use as long as they have the means to communicate on that frequency. Yeah. But the disadvantage of what would be a disadvantage of the unlicensed spectrum from licensed spectrum? A lot of interference, right? Because anyone can just tap into that unlicensed spectrum. On the other hand, for licensed spectrum, only approved operators can operate on them, right? So you see different type of spectrums, different multi-accessing schemes being used. Okay, to support diverse service categories and devices, right? As we already mentioned. Okay, another important innovation at the radio access level is the so-called dynamic RAN, right? So here the radio access network is created to be capable of adapting to rapid changes in the user demands and diverse mix of 5G service categories. Okay. So here, you can see different techniques that are being used to support ultra dense networks, something like uh, adding small cells dynamically into the macro cell, right? Um, you see concepts of moving networks where uh, mobile nodes are used to serve users in high mobility, right? Or you can sometimes you see nomadic nodes to serve users in unpredictable locations. Okay. To support this dynamic RAN network, okay, some multiple antenna techniques are also used. In addition to dynamic RAN, 5G also deploy dynamic spectrum sharing, okay, enable efficient sharing of spectrum, okay, to share suitable frequency bands to maximize spectrum utilization and reduce the cost and speed up the deployment for different operators. Okay. Another innovation in 5G is the direct communication, sometimes called device to device communication. So here is like Bluetooth communication, right? But this one is part of a 5G protocol. So again, like edge computing, right? This is there to basically reduce frequent latency, right? And also offload some traffic from the core network when feasible, right? And if you upload some suitable communication to device, then overall the spectrum is more effectively used by all the users. Okay. Another added benefit is the direct communication, right? They can function independently of the core network infrastructure that can be useful for the disastrous situation of outage and emergency, right? So we mentioned a little bit about this of improving the control plane, okay, to further reduce the latency, right? So here again, control plane is about handshaking, right? The bulkier it is, okay, many more rounds of handshaking are required, thereby yielding larger latency. If you want to reduce the end-to-end latency, you need to make the control plane leaner, okay? And this comes with important characteristics like reduce overhead because you want to reduce handshake, right? Reducing the interaction in the control plane also means improving the energy efficiency, right? This can be particularly useful, okay, for certain applications like URLLC, right, that require very low latency, or MMTC that requires a very long lasting battery life. Okay. So here, several techniques can be used like broadcasting, you tune reference signals, you enhance the sleep modes. Um, so in some case, you can even combine or separate control plane user plane using the combined one or separate one leaner, right? Depending on the use. Okay, last one we mentioned about the key enabler for 5G is the so-called toolbox, right? Why do we need a spectrum toolbox? Because as you saw, right, 5G is using a lot of spectra or spectrums, right? Um, and even more importantly, when the operators are going to new countries or new geographical area, okay, the regulatory environments are different, right? So oftentimes you need to integrate the spectrums to be used for a specific operator differently depending on the area. So that's why having this toolbox, okay, will be very useful for the operator in scaling their deployment across different geographical regions, right? Because this toolbox will um, allow operation in wide-ranging bands and bandwidths to be integrated efficiently, and also enable different sharing scenarios with other operators. Okay, and it will also help the operators to conform with the different regulatory environments for different countries. Okay, any question, comments? You need another break or you want to keep going? Do you need another break? Small break? We have only one more topic to go. Do you need another break or you want to keep going? Keep going? Okay. So last thing, we have to talk about the overall architecture. Okay. Again, like 4G and 3G that we discussed, right? The entire architecture, okay, consists of the edge and the core, right? At the edge are the user equipments, right? And the RAN or radio access network, right? That's the part of the sub network starting from the base station going to the end devices, right? Every time you go to a next G, you see a new jargon, right? Remember In 4G, we call this base station E node B, right? Somehow for 5G, they are called G node B. I don't know why. Next generation node B. Don't ask me, okay? And then for the core network, you see a lot of components reminiscent to what you saw in 4G, right? Something like AMF, Access Mobility Management Function that handles UE registration mobility. What does this remind you of? AMF in 4G, it is tantamount to what? What entity? You just did the quiz, right? Remember MME, right? This AMF is like MME. Yeah. For 5G, they just call them differently. Okay. Uh, what about SMF, Session Management Function? Keyword is IP address allocation. So what does that remind you of in 4G? Which entity allocate the IP address to the user UE? Huh? Which entity in the core network allocate IP addresses to the UE? P gateway, right? So then you see something like UDM, Unified Data Management, store subscriber and device data. What does that remind you of in 4G? Which entity of the 4G core network store your subscription information? Is the HSS, right? Home subscriber system or service, right? So you see these different entities in the 5G architecture, right? Okay. But I would say they are quite similar to the different entities in 4G core network. Just that some of the function may be splitted out into a dedicated device, like dedicated entity like AUSF is authenticated to only authentication, right? Yeah, because there is significant updates to 5G, right? From 4G. In particular, the the new radio in 5G, it is not compatible with 4G. By that I mean, if you have old phone, right, that support only 4G, meaning your cellular chip inside the smartphone doesn't support 5G, then you cannot connect to 5G network, right? So that's why in the deployment of the real 5G, you see that deployment happen in phases, right? By first um, doing the incremental deployment by piggybacking on the old 4G network before going to the full deployment. This is called non-standalone in the incremental deployment and later on standalone, right? So what do I mean by non-standalone 5G? This is a deployment of 5G networks, okay? Uh, that still rely on the 4G infrastructure for the control plane, okay? For signaling, the only part of 5G that is deployed in the non-standalone deployment mode is the radio, right? The new radio in 5G is only deployed for the user plane, right? Where the control plane is still being piggybacked into the old control plane of 4G. Okay. And this, of course, allows the network operators to deploy it faster because the 4G is already running, right? You just need to adapt it to support this new radio, right? To enable this deployment. Okay. So in this deployment mode, you see that the connectivity is dual, right? Where the user can select either the new radio or the old radio to connect to the old control plane. Okay. And as a consequence, operators can roll this out quicker with lower cost, right? But the drawback is that you don't get the full benefits of 5G, right? Because you don't use its control plane yet. Okay. The full deployment is called standalone. Okay. Is to additionally use the core network of 5G for the control plane. Okay. Which will enable multiple features like lower latency, okay, network slicing, and other enhanced capabilities of the full 5G network, right? But of course, it is costlier to deploy 5G in the standalone mode because you have to build new infrastructure, okay, and also the new core network in addition to the infrastructure for the new radio, right? In addition, you also the operators also need to deploy and manage these cloud native cores to enable important features like network slicing and edge computing. So as I said, 5G and 4G are not compatible, right? So at any point in time, okay, you want to connect to 5G because it's the best, right? But uh, when 5G is not available, uh, you need an extra capability to connect to 4G as well. So if you have newer devices, you have basically two chips, right? One for 5G, the other one for 4G to roll back to 4G. Okay. But if your devices are older and only support 4G, that means you cannot connect to 5G. So again, the difference here is in the control plane. For the non-standalone, right? The control plane is done over the 4G core network, right? For the standalone, because you already moved to the 5G core, there's no need to use 4G radio anymore, except for uh, cases, emerging case of aggregation that I will speak about shortly. But of course, the standalone deployment requires higher capital investment, right? But this investment will come with extra benefits, right? Like reducing the latency further and enable important uh, network function like network slicing and others. Okay. So here is a picture of uh, coexisting connectivity in the current network environment, right? So you see 5G, you see 4G as well, right? So how do you connect? Okay. So like 5G, you see for smaller cells employing the millimeter wave band, that's 5G, right? And but for other cases, you may be connected to uh, older networks, right? So in modern device, you see multimodal connection, right? That can connect you to any possible networks 5G, 4G, 3G, or Wi-Fi, right? And basically, at a particular area, it will just select the best one, right? So you can see here 5G radio access below 6G using LT anchor. This is like the non-standalone uh, deployment, right? And then this one using the 5G core network is like the standalone uh, deployment. So you see like same device can connect to many networks, right? Depending on where the device is located. Okay, just to summarize, right? We review the evolution of the subsequent cellular network generations, right? Then we focus on the current generation 5G, in which we discuss important service categories, three of them: EMBP, MMTC, URLLC, right? And different technology enablers that will allow the 5G to be made to be suitable for these widely diverging application areas. Right? So 5G is a transformative technology that is supposed to be the enabler of more and more challenging applications as the network evolves. These enabling technologies will continue to play a crucial role, okay, to make the network more scalable and more efficient. Okay. And then when the time comes, it will be appropriate for the community to introduce yet another generation of cellular network that we call 6G. That's all going in terms of research. Okay. And you should expect it to materialize within the period of about 5 to 10 years. Okay. So here's some more references on the material of this deck if you want to go a little deeper. Okay, so I think now it's a